Hey Geometry Crowd, post a quick little video going through our notes. I would suggest following along, taking the notes with me, and then you can do the practice problems on your own, which will be a separate attachment. So let's talk about finding the area of polygons. So we have regular polygons, right? Notice by definition, as a regular polygon is all equal sides, all equal angles, and the maximum lines of symmetry for that particular number of sides. And my question for you guys to pose is, how could you find the area of a regular polygon? And the hint is they all have something in common. Well, the way to find the area of a regular polygon is actually going to be kind of our leading question for this entire thing today. So keep this question in mind. We're going to be coming back to it. And the hint is knowing that having equal angles and equal sides will come into play. All right, so let's look at some of the examples now. So you turn over, it says central angle. This is actually part of how we're able to find this area of a polygon. The central angle of a regular polygon is formed by two lines from consecutive vertices. Down here it says the measure of each central angle of a regular polygon is 360 divided by n. And 360 represents the sum of the measures of the central angle in the polygon. And n represents the number of vertices in the regular polygon has. That sounds a little complicated, but here, let's make it real easy. The central angle is drawn like this. I'll do the square because it's very easy to see. We could do this example with any of the shapes though. Central angle is constructed like this. We draw lines from each vertex to the center. All right, sorry the line's a little crooked there. To find a central angle, we actually just kind of envision something like this. I'm just drawing a circle right here. Well, we had a circle right here, and I asked you to find what's this angle in that middle, the central angle right there. Well, a circle is 360 degrees, and this is cut into 4 slices. So it'd be 360 divided by 4. That's where we're getting this out from. 360 divided by n. Whatever the number of sides are, we divide 360 by that. That helps us find our central angle. So down below, it asks us to find the central angle of each of the following figures. Well, we can do this pretty quickly. It's always 360 divided by the number of sides. So for a triangle, it's going to look like 360 divided by 3. For a square, it's going to look like 360 divided by 4. For a pentagon, it's going to look like 360 divided by 5. And for a hexagon, 360 divided by 6. We can then go ahead and simplify to find the central angles of 120, 90, etc. Right? So you guys kind of fill those out. You guys can fill in those completed answers as well. This is where we really want to get to today. Okay? Finding the area of a regular polygon. So some of the vocab we're going to need to know for regular polygon is up top at your notes. Read those, familiarize yourself. Something new is this word apothem. Apothem is that kind of that height of that triangle we see right there. So we're going to know the height of the triangle to find the area of that little triangle. So I'm going to show you guys a proof for how we get to the formula for the area of a regular polygon. We're going to use this hexagon as an example. Now, I know the formula is down at the bottom of the page. This little proof just to demonstrate how we get to that formula. And then for our examples today, we're just going to be applying this formula. But this is the why behind it. All right? Well, if I want to find the area of this hexagon, or really any polygon, I can find the area of this triangle and then multiply it by how many triangles would fit. Because really, I could copy and paste this triangle 6 times around. It would fill up the entire area of that hexagon. So the area of one triangle times the number of triangles that would fit in our given polygon. In this case, it's a hexagon, so 6 triangles will fit in there. Now, let's actually put some numbers to this problem. If we said the area would be of a triangle is 1/2 base times height. Now, in this case, we have the height labeled as A. Again, A representing the apothem. Well, that's the area of a triangle. We said the area of this hexagon would be the same amount of area that these triangles would take up, or 6 total triangles. So you can multiply this by 6. What I mean by I keep saying, if I kind of copy and paste this triangle, over and over again, I could fit in, almost knocked over the camera there, I could fit in 6 of these triangles. Those are the 6 triangles that we would say. So I'm actually just going to keep this form, but just do a little rearranging. So even though this is the area of one triangle and there's 6 total triangles, which will equal the total area of the shape. Well, look if I rearrange it a little bit and write 1/2 times A times B times 6. Okay, nothing fancy there. That's just a commutative property. We're allowed to rearrange things with a commutative property. But I want to focus in on this right here. B times 6. Well, B is this base of this triangle, but it's also the side length of this regular hexagon. Well, 6B. 6B is 6 times B, or in terms of regular hexagon, which this shape is, 6B, if I label some B's around this, is actually the value of the perimeter. So B times 6 is really the perimeter of that polygon. The area of a regular polygon is 1/2 A, which stands for apothem, times the perimeter. That's further outlined down below in that gray text box. All right? Well, now that we see where we get this formula from, specifically this formula down here, let's apply it. All right. So I'm going to do these first 3 problems up here with you guys. All right? So let's find the area of a regular polygon. In this case, a hexagon, a square, and an equilateral triangle. We're going to be using our relationship on special right triangles. All right, so I'm going to be referencing 30, 60, 90 triangles as well as 45, 45, 90 triangles. You may want to go back and review those. A hexagon with an apothem of 7 rad 3. Here's my apothem. I'll go ahead and label that right there. Well, this is a hexagon. I actually know some of the values of the angles in this little triangle right here. This is a 90-degree angle. I can just put that right there. We know the height. This is 30 degrees and this is 60 degrees. And I can explain why real quick. The central angle of a hexagon is 60. Well, this is half of that triangle. So that central angle is really just cut in half there. So the central angle of a hexagon is 60. That 30 is half of 60. Now, in a 30, 60, 90 triangle, there's a relationship. 30, 60, 90 triangle. Again, I highly recommend maybe looking that back up if you're not sure. In a 30, 60, 90 triangle, if I want to move from the 60 side to the 30 side, all I have to do is divide by radical 3. Therefore, I would know that side is 7. Now I can calculate the area of this hexagon. If this side is 7, by the way, that means the entire side length is 14. Again, because 7 plus 7 is 14. So to calculate this value, it would be 1/2 times the apothem times the perimeter, which is 14 times 6, which comes out, I'll just put it like this actually. Now we do this calculation, 1/2 times 7 radical 3 times 14 times 6. That would actually come out to be 294 radical 3. Notice I have E there to represent I want an exact answer, meaning I don't need to type out this radical 3. So I'm using a calculator where I'm really typing is 1/2 times 7 times 14 times 6, and calculating that as 294. Radical 3 is almost treated like a variable, so we just attach it at the end. And the last thing we'll attach is our proper unit, so centimeters squared. Well, let's check out how we do the square example now. The square example has a radius of 4 radical 2. Remember, the central angle of a square would be 90 degrees. That would make that this is a 45, 45, 90 triangle. Again, that angle on the top is half of my central angle. Well, 45, 45, 90 triangles have a special relationship as well. If I have the hypotenuse, I can calculate the apothem or the base, because of the same value in a 45, 45, 9 triangle, as 4, simply by dividing by radical 2. To calculate the area, now I would calculate 1/2 times 4, or the apothem, times the perimeter, which is 8 times 4. Again, this whole side is really 4. So 8, 8, 8, 8, 8 times 4. All right, they calculate this. We again 1/2 times 4 times 8 times 4. We would get 64 centimeters squared. Okay, moving on to our triangle example. We have an equilateral triangle with a side of 18. Well, if the entire side is 18, let's draw that. I'll write up here. If the entire side is 18, that would imply that that portion right there is 9. Also, we know the angles. Hint, it's always going to be a special right triangle. We're going to have 60 degrees right here and 30 down below. Again, the reason why the central angle of a triangle is 120 degrees. Half of that angle is 60. That's where we're going to have 60 right there. Now to finish this problem off, I want to calculate the apothem to determine, because I'm going to need the apothem to help me calculate the area. So the apothem, if I want to go from the 60 side to the 30 degree side, I have to divide by radical 3. So 9 divided by radical 3. Now I'm going to go ahead and rewrite that because we like to rationalize our answers and not have a radical expression in the denominator. So we're going to go ahead and multiply top and bottom by radical 3. And I would get apothem is 9 radical 3 over 3, or 3 radical 3. Again, A for apothem. To calculate the area, we're going to do 1/2 times the apothem times the perimeter. 1/2 times the apothem times the perimeter. Now the perimeter is 18 times 3, right? 18, 18, 18. So we're going to calculate the perimeter. Type this in as 18 times 3. To determine the final answer, notice it has an exact with it. We can calculate this as 1/2 times 3 times 18 times 3. Notice I'm not going to include that radical 3. Okay, we're not going to include that. And we would get 81 radical 3 centimeters squared. So that's how we kind of work through problems like that. Down below, I didn't show the work, but I put the answers right there. Challenge yourself. See if you can practice these and see if you can get these answers well. I'm not requiring you to submit this portion. However, go ahead and do the practice problems now and refer back to this video or the extra video links if you need any extra help. Have a good one, guys.